Greetings and salutations, magical chemists. Today we're going to talk about gravimetric analysis, which is a lab-stoic procedure in which you precipitate out a specific ion of interest to find the percent mass of that ion in an impure substance. As far as laboratory technique is concerned, it is a very straightforward three-step process. First, you have to react that impure material with the known compound, and the goal is to form a precipitate that contains the ion you are trying to isolate. Next, you need to figure out how much precipitate you have. So you filter it, dry it, and measure the mass. And once you have your data of the mass of the precipitate, you just get to use delicious stoichiometry to work backwards to calculate, well, I have the mass of this precipitate containing an ion. Let me work backwards to figure out the mass of the specific ion that I'm looking for. And that's it. Now, there are a couple of steps along the way to help minimize lab error. So let's look at that in a little more detail. Okay, first, you need to know how much of your impure sample you're starting with. So you want to make sure that it's completely dried and you get the mass. And then you're going to dissolve that sample into water. This technique only works if you are starting with something that is soluble and impure. Next, you want to precipitate out all of the ion you're trying to study. So it is very important that you add your precipitating reagent, basically the other reactant that you're trying to cause the precipitation reaction, add it in excess, like extreme excess. You want to make sure that the impure sample is your limiting. After we've had that reaction, now we need to filter the precipitate. We need to remove it from solution. So that's what this image is showing over here. So what you start off with is your mixture of solid and liquid, right? This has your precipitate, but it's also mixed up with the aqueous ions. And you're gonna pass that liquid through, so there's a funnel with a piece of funnel paper in it. Honestly, kind of like a coffee filter, and it's trapping the solid particles, letting everything else that is aqueous pass through. Because this is chemistry, we have a special word for that, all the aqueous stuff that passes through and doesn't get trapped. It's called the filtrate, the stuff that was filtered. And then, of course, the idea is the precipitate is what should be trapped up in the filter paper. There is a step we add to make sure that some of the aqueous ions haven't gotten kind of trapped up in the filter paper. We actually are going to wash the precipitate, which sounds really weird, but we're not going to use like soap or anything. It literally just means rinse with deionized water. Once you're done, you've washed your precipitate. Now you got to let it dry, which can take a little while. Drying ovens are helpful. And once it is dry, you're going to make sure it's dry by weighing it to constant mass. So that's what it looks like in the lab. But, our tests are on a piece of paper. So in that case, we're just manipulating the data given. So the kind of chemistry and math steps for gravimetric analysis honestly always follow the same three steps. It's very convenient. First, you need to write the balanced precipitation reaction, because unless you know the ratio between the precipitate and the ion you're looking for, this is going to be kind of challenging. So once you have that lovely balanced precipitation reaction, you're gonna use stoichiometry to convert from the mass of your precipitate to the mass of the ion of interest. Then most of the time what you're trying to figure out is what percent by mass was my original impure sample? So you just take the mass of the ion that you calculated and divide it by the mass of the original impure sample. Let's go ahead and try an example problem to see what this might look like. In this example, we collected data when we had an unknown alkali metal chloride, and we basically reacted it with something that had silver in it, because that will form a precipitate of silver chloride. So we measured the mass of the watch glass. That's just the container, basically. And then you get the mass of your unknown chloride sample, that's your impure stuff, with the watch glass. And then at the end, you have the mass of the precipitate that was formed, the silver chloride, and, it's still on the watch glass. So this honestly is very similar to some of those hydrate calculations we did, because we're doing chemistry, getting rid of the water, making another mass measurement. But you do have to be careful and subtract away the mass of the watch glass. So in this case, for the very first one, you want to calculate the mass of the precipitate. Well, that's just the mass of the precipitate and the watch glass minus the watch glass. which, of course, you are totally going to show your work for, even though it's only subtraction. For sig figs, notice that you're subtracting, so we care about place value. And both of these numbers are significant to 4 places after the decimal, so conveniently enough, that's exactly how we get to keep our answer. Okay, well now we know the mass of silver chloride. I want to find the mass of just chloride ions. And this is just one of those whole to part calculations that we were working on in Unit 1. So you actually already know how to do this. So you should go ahead and pause the video and try it on your own. And when you are ready to check, unpause the video. Well, if you want to convert from the whole silver chloride precipitate into just chloride, that's a mole-to-mole conversion. So we have to convert to moles first. But once we're in moles of silver chloride, conveniently enough, well, in every 1 formula unit of silver chloride, there's exactly 1 chloride ion. And yes, the chloride ion is negative. Now you want to convert to mass, so we need the grams of a chloride ion in 1 mole. But remember, it gained an electron, but electrons have negligible mass. So this is just the mass of chlorine. And that's the whole setup. Don't forget to watch out for sig figs. We are starting with 4 sig figs. So that means your final answer, once you do all the calculations, is going to have 4 sig figs as well. The last question says, okay, if that's how many grams of chloride ions you had in the original sample, what is the percent by mass of chloride ions in the original sample? Well, first, we have to know how much sample we had, right? And the only mass we have is the mass of the sample on a watch glass, so we better subtract the mass of that watch glass. Now we know the mass of the chloride, and we know the mass of the total sample, so very straightforward, plug into the percent, equation. When you subtracted for the mass of the sample, because of place value, you only got 3 sig figs, so your final answer will have 3 sig figs. Just realized I made a small error. A lot of times the sample is impure in gravimetric analysis. But in this problem, it actually wasn't an impure sample, it was just an unknown sample because we had an unknown alkali metal chloride and we were trying to figure out, well, which one is it actually? Well, through all of our delicious math, we discovered that our sample was 47.6% chloride by mass. Well, now, if you want to try to figure out which one of these it is, you kind of just got to check the percent by mass of chloride for each of these and see which one matches up. I like to pick one of the ones in the middle and then see if I have to go higher or lower so I don't have to calculate all 4 of them. For example, sodium chloride. Well, sodium chloride has 1 chloride, so 35.45 grams. And so based on the molar mass of chlorine compared to the molar mass of sodium chloride, it turns out this one is 60.7% chloride by mass. Well, that can't be the one we want, right? We want one that is 47.6%. So, nope, sodium chloride, it's not you. Okay, we need something that is a smaller percent chloride by mass than sodium chloride. Well, that means it can't be lithium chloride, right? Because lithium weighs even less than sodium. That would have an even higher percent by mass of chloride. So let's check KCl and see where we're at. Well, it turns out the potassium weighs a bit more than the sodium did, right? So this lowered the percent chloride by mass. And hey, look, it is exactly what we were looking for, 47.6% by mass of chloride. So our unknown must be tasty and delicious potassium chloride. Okay, so that's one example of kind of the basic gravimetric analysis math stuff. As you can imagine, there are lots of delicious lab errors that we can discuss in the context of this lab. So let's go ahead and take a look. Okay, first, you forgot to add enough precipitating reagent, or maybe you miscalculated, or something. But if you don't add enough of the stuff that's going to form the precipitate, some of your ion won't precipitate. So not all of it will precipitate. And if it doesn't all precipitate, it won't show up in the mass. And so if the mass is too low, the calculated percent of that ion by mass will also be lower than the actual percent of the ion by mass. Let's say you had a hygiene error, failure to wash. Well, in failure to wash the precipitate to remove those soluble impurities. That means some impurities are probably still stuck in the precipitate. So when you measure the mass is going to have the precipitate, but it's also going to have extra stuff, so it would weigh more than it should. So when you calculate the percent by mass of your ion, it would be higher than it should be. Now, it's important to wash the precipitate, but you don't want to excessively wash it, And you don't want to wash it with warm water because that's more likely to dissolve away some of the precipitate. It's okay, yes, the precipitate is insoluble, but technically you can still dissolve small parts of it. And as small parts of the precipitate dissolve into the wash and get carried into the filtrate, they are not measured in the mass of the precipitate and thus not calculated in the calculated ion percent by mass. This, of course, means your ion percentage will be lower than it should be. Now, just like in the hydrate lab, it is possible for your precipitate to not be fully dried. Honestly, we've had that trouble if it's really humid out. It takes a long time to dry. So if it is not dried to constant mass, well, when you measure the precipitate mass, you're also measuring some molecules of water, which makes the mass of the precipitate higher than it should be. So the calculated ion percent by mass will also be higher than it should be. Okay, so that's a fun table of lab errors. Let's go ahead and try one more practice problem together to see if this is making any sense. The first step of this problem is mathy math. Yum. So at this point in time, you should possibly know how to do this. So if it is making any sense, pretty please pause the video and go ahead and try. Honestly, even if it's not making sense, try something. And when you're ready to check your answers, unpause the video. Okay. First, we need to kind of extract the numbers that we need, right? You got so many grams of an impure sample containing sulfur and soluble inert material. By the way, inert means does not react, so that would not be part of a chemical reaction. So we dissolve our impure sample in 350 ml of water, and then we are going to precipitate. So the sulfur got converted to sulfate. We precipitate sulfate with barium, forming barium sulfate, and we, dry it, measure the mass, all that stuff. So to find the mass of sulfur, the key is that you always have to start not with your original impure sample, because you don't know how much sulfur's in there. You have to start with the mass of your precipitate. That's always the place to start. So we need to convert from barium sulfate into just sulfur. That means we need to convert to moles, and, well, turns out there's only one sulfur in barium sulfate, so it's a 1-to-1 mole ratio. And then we can use the molar mass of sulfur to find grams of sulfur. So keeping the 4 sig figs we started with, we find that there was 0.2754 grams of sulfur in the original compound. And if you want to find the percent by sulfur in the original ore, well, you just take the sulfur you have and divide it by the mass of your original sample. And it turns out we've got a pretty small percentage by mass of sulfur, right? It's only like 8.641% sulfur. All right, so that was the math. And now let's take a look at a couple of error analysis questions. The first one wants to know, well, if a small amount of the barium sulfate precipitate dissolved while being rinsed, what effect would this have on the calculated percent by mass of sulfur? The second one wants to know, well, okay, what if the originally impure sample was originally dissolved in 500 milliliters of water instead of the 350 that it was originally? What effect would that have? And you know what? You're going to try these because this is definitely somewhere we all need practice, making sure we can efficiently but specifically answer error analysis. So please pause the video, take a moment, and then we'll go over the answers. Okay, in part C, the important part to realize is that if some of the precipitate dissolved into the filtrate, it's not going to be measured in the precipitate mass. And of course, if the measured mass of the precipitate is too low, or lower than it should be, the calculated percent by mass of sulfur will also be too low. Now in the second problem, we're looking instead about changing the amount of water that we're dissolving the original sample into. What's interesting is that the water, the amount of water, doesn't actually change any of our calculations, right? We use the water because we have to dissolve stuff and form a precipitate, but then we filter it away and we dry to constant mass. The water, regardless of how much there is, should be gone by the end. So adding extra water will not have an effect on the amount of sulfur present, so it's not going to affect the calculated percent by mass of sulfur. So there you have it, gravimetric analysis in all of its mathy and error analysis glory. Error analysis glory, none of those sound right. But either way, thank you for playing with the glories of chemistry.